A spaceplane is an aerospace vehicle that operates as an aircraft in Earth's atmosphere, as well as a spacecraft when it is in space. It combines features of an aircraft and a spacecraft, which can be thought of as an aircraft that can endure and maneuver in the vacuum of space, or likewise a spacecraft that can fly like an airplane. Typically, it takes the form of a spacecraft equipped with wings, although lifting bodies have been designed and tested as well. The propulsion to reach space may be purely rocket-based or may use the assistance of air-breathing jet engines. The spaceflight is then followed by an unpowered glide return to landing. Only 5 spaceplanes have successfully flown to date, having re-entered Earth's atmosphere, returned to Earth, and safely landed: the North American X-15 Space Shuttle, Buran, Spaceplane, and Boeing X-37. All 5 are considered rocket gliders. As of 2015 update, only these aircraft and rockets have succeeded in reaching space. 2 of these 5 are rocket-powered aircraft, having been carried up to an altitude of several tens of thousands of feet by an atmospheric mothership before being released, and then flying beyond the boundaries of the Earth's atmosphere under their own power. 3 are vertical takeoff horizontal landing vehicles relying upon rocket lift for the ascent phase in reaching space and atmospheric lift for re-entry, descent and landing. The 3 VTHL spaceplanes flew much further than the aircraft-launched ones, not merely leaving the Earth's atmosphere but also entering orbit around it, which requires at least 50 times more energy on the way up and heavier heat shielding for the trip back. Also, of the 5 vehicles, 3 have been piloted by astronauts, with the Buran and X-37 flying unmanned missions. Description: significant features distinguish spaceplanes from spacecraft. Aerodynamic lift: all aircraft utilize aerodynamic surfaces in order to generate lift. For spaceplanes, a variety of wing shapes can be used. Delta wings are common, but straight wings, lifting bodies and even rotorcraft have been proposed. Typically, the force of lift generated by these surfaces is many times that of the drag that they induce. Atmospheric re-entry: because suborbital spaceplanes are designed for trajectories that do not reach orbital speed, they do not need the kinds of thermal protection orbital spacecraft require during the hypersonic phase of atmospheric re-entry. The Space Shuttle thermal protection system, for example, protects the orbiter from surface temperatures that could otherwise reach as high as 1,650 degrees Celsius, well above the melting point of steel. Aircraft landing: a spaceplane operates as an aircraft in Earth's atmosphere. Aircraft may land on firm runways, helicopter landing pads, or even water, snow or ice. To land, the airspeed and the rate of descent are reduced such that the aircraft descends at a slow enough rate to allow for a gentle touchdown. Landing is accomplished by slowing down and descending. This speed reduction is accomplished by reducing thrust or inducing a greater amount of drag using flaps, landing gear or speed brakes. Splashdown is an easier technical feat to accomplish, requiring only the deployment of a parachute, rather than successfully aviating the atmosphere. Project Gemini's original concept design was as a spaceplane, with paraglider and wheels attached. However, this concept was abandoned in favor of parachute splashdowns, because of expensive technical failures during testing and development. Whereas Project Gemini's splashdown parachutes took only 5 months to develop in 1963. Gemini's spaceplane concept failed to materialize even after nearly 3 years of continued development. Propulsion rocket engines: all spaceplanes to date have used rocket engines with chemical fuels. As the orbital insertion burn has to be done in space, orbital spaceplanes require rocket engines for at least that portion of the flight. Air-breathing engines: a difference between rocket-based and air-breathing aerospace plane launch systems is that aerospace plane designs typically include minimal oxidizer storage for propulsion. Air-breathing aerospace plane designs include engine inlets so they can use atmospheric oxygen for combustion. Since the mass of the oxidizer is, at takeoff, the single largest mass of most rocket designs, this provides a huge potential weight savings benefit. However, air-breathing engines are usually very much heavier than rocket engines and the empty weight of the oxidizer tank, and since, unlike oxidizer, this extra weight must be carried into space, it may offset the overall system performance. Types of air-breathing engines proposed for spaceplanes include scramjet, liquid air cycle engines, pre-cooled jet engines, pulse detonation engine, and ramjets. Some engine designs combine several types of engines features into a combined cycle. For instance, the rocket-based combined cycle engine uses a rocket engine inside a ram scoop so that at low speed, the rocket's thrust is boosted by ejector augmented thrust. It then transitions to ramjet propulsion at near supersonic speeds, then to supersonic combustion or scramjet propulsion, above Mach 6. Then back to pure rocket propulsion above Mach 10. Harsh flight environment. The flight trajectory required of air-breathing aerospace vehicles to reach orbit is to fly what is known as a depressed trajectory, which places the aerospace plane in the high-altitude hypersonic flight regime of the atmosphere. This environment induces high dynamic pressure, high temperature, and high heat flow loads, particularly upon the leading-edge surfaces of the aerospace plane. These loads typically require special advanced materials, active cooling, or both, for the structures to survive the environment. Rocket-powered spaceplanes also face a significant thermal environment if they are burning for orbit, but this is nevertheless far less severe than air-breathing spaceplanes. Suborbital spaceplanes designed to briefly reach space do not require significant thermal protection, as they experience peak heating for only a short time during re-entry. Intercontinental suborbital trajectories require much higher speeds and thermal protection more similar to orbital spacecraft re-entry. Center of mass issues. A wingless launch vehicle has lower aerodynamic forces affecting the vehicle, and attitude control can be active, perhaps with some fins to aid stability. For a winged vehicle, the center of lift moves during the atmospheric flight as well as the center of mass, and the vehicle spends longer in the atmosphere as well. Historically, the X-33 and HOTOL spaceplanes were rear-engined and had relatively heavy engines. This puts a heavy mass at the rear of the aircraft with wings that had to hold up to the vehicle. As the wet mass reduces, the center of mass tends to move rearward behind the center of lift, which tends to be around the center of the wings. This can cause severe instability that is usually solved by extra fins which add weight and decrease performance. Flown spaceplanes. Orbital spaceplanes. All three of the orbital spaceplanes successfully flown to date utilize a VTHL design. They include the piloted United States Space Shuttle and two unmanned spaceplanes. The late 1980s Soviet Buran and the early 2010s Boeing X-37. The early 1980s Bor-4 was a spacecraft that did successfully re-enter the atmosphere and fly like an aircraft. But it was not designed to sustain atmospheric flight. It was designed to stop flying, open a parachute and then splash in the ocean. These vehicles have used wings to provide aerobraking to return from orbit and to provide lift, allowing them to land on a runway like conventional aircraft. These vehicles are still designed to ascend to orbit vertically under rocket power like conventional expendable launch vehicles. One drawback of spaceplanes is that they have a significantly smaller payload fraction than a ballistic design with the same takeoff weight. This is in part due to the weight of the wings, around 9 to 12% of the weight of the atmospheric flight weight of the vehicle. This significantly reduces the payload size, but the reusability is intended to offset this disadvantage. While all spaceplanes have used atmospheric lift for the re-entry phase, none to date have succeeded in a design that relies on aerodynamic lift for the ascent phase in reaching space. Efforts such as the Silber-Vogel and X-30, X-33 have all failed to materialize into a vehicle capable of successfully reaching space. The Pegasus winged booster has had many successful flights to deploy orbital payloads, but since its aerodynamic vehicle component operates only as a booster, and not operate in space as a spacecraft, it is not typically considered to be a spaceplane. On the other hand, OREX is a test vehicle of HOPE-X and launched into 450 km LEO using H2 in 1994. OREX succeeded to re-enter, but it was only hemispherical head of HOPE-X, that is, not plane-shaped. Suborbital spaceplanes. Other spaceplane designs are suborbital, requiring far less energy for propulsion, and can use the vehicle's wings to provide lift for the ascent to space in addition to the rocket. As of 2010, the only such craft to have successfully flown to and from space, back to Earth, have been the North American X-15 and Spaceplane. Neither of these craft was capable of entering orbit. The X-15 and Spaceplane both began their independent flight only after being lifted to high altitude by a carrier aircraft. Scaled composites and Virgin Galactic unveiled on December 7, 2009, the Spaceship Two spaceplane, the VSS Enterprise, and its White Knight II mothership, Eve. Spaceship Two is designed to carry 2 pilots and 6 passengers on suborbital flights. On 29 April 2013, after 3 years of unpowered testing, the spacecraft successfully performed its first powered test flight. XCOR Aerospace signed a $30 million contract with Yechen Aerospace Center to build and lease its Lynx Mark II spaceplane, which would be designed to take off from a runway under its own rocket power, and to reach the same altitude and speed range as Spaceplane and Spaceship Two. Due to the fact that Lynx is propelled by higher specific impulse fuels, Lynx is designed to only carry a pilot and 1 passenger, although tickets are expected to be around half those quoted for Virgin Galactic services. HyFlex was a miniaturized suborbital demonstrator of HOPE-X launched in 1996. HyFlex flew to 110 km altitude and succeeded in atmospheric re-entry, subsequently achieving hypersonic flight. Though HyFlex achieved a controlled aircraft descent, it was not designed for a planned aircraft landing, the engineers opting instead for a splashdown without a parachute. The HyFlex that flew failed to recover and sank in the Pacific Ocean.